11 billion miles from where you are sitting right now in a place so cold and so empty that scientists once assumed nothing could ever really happen there, something rang. Not a radio broadcast, not a malfunction. A clean, measurable tone picked up by an instrument built in the 1970s, still working, still listening, decades after everyone who built it assumed its job would already be finished. On January 30th, 2019, NASA's Voyager 2 spacecraft, drifting through true interstellar space for the very first time in its history, caught a frequency ringing through the darkness around it, a frequency that had no business existing according to almost everything scientists thought they understood about the edge of our solar system. And when researchers finally figured out exactly what that frequency was, and more importantly, what was causing it, it became one of the strangest, most quietly unsettling confirmed discoveries to come out of the entire Voyager mission. This is that story. By the time it's over, you're going to think differently about the silence between the stars. Let's start with where Voyager 2 actually was when this happened, because the location changes everything about why this discovery matters. Voyager 2 launched from Cape Canaveral on August 20th, 1977, 16 days before its twin spacecraft, Voyager 1. Both were built to take advantage of an extraordinarily rare alignment of the outer planets, one that occurs only once every 175 years, allowing a single spacecraft to use the gravity of each planet to slingshot itself toward the next. Voyager 2 was sent on the more ambitious path, flying past Jupiter, then Saturn, then Uranus, then Neptune, becoming the only spacecraft in human history to visit all 4 giant planets up close in a single continuous mission. It gave us our only detailed images of Uranus's sideways tilted rings and its pale, oddly featureless surface. It discovered new moons around the ice giants that nobody knew existed. And in the summer of 1989, it captured the only close-up photographs of Neptune that humanity has ever taken, images that remain, decades later, our sole direct look at the outermost planet in our solar system, its great dark spot, and its strange, geyser-like moon Triton. When that planetary tour finally ended, most people watching from Earth assumed Voyager 2's historic career was over, its job complete, its usefulness winding down toward a quiet retirement. It wasn't. Its most important, most genuinely strange work hadn't even started yet. Because past Neptune, Voyager 2 kept going deeper into the dark, chasing something far bigger and far less visible than any single planet, the actual edge of the sun's influence itself. Here's something most people never really stop to think about. Our entire solar system sits inside an enormous invisible bubble. The sun doesn't just produce light and heat, it constantly exhales, throwing out a relentless stream of charged particles called the solar wind, blasting outward in every direction at speeds up to 1,000,000 miles an hour, non-stop, every second, for the past 4.5 billion years. That outward pressure inflates a colossal bubble around the sun and every planet orbiting it, a bubble scientists call the heliosphere. Everything you've ever known, every planet, every moon, every spacecraft humanity has launched, exists inside this bubble, partially shielded from the far more violent radiation drifting through the rest of the galaxy. Eventually, far beyond the orbit of Pluto, the outward push of the solar wind fades enough that the pressure of true interstellar space, the actual physical material filling the gaps between stars, takes over completely. That transition point is called the heliopause, and physically crossing it means leaving the solar system behind for good, stepping into a region of space governed by entirely different physics. Voyager 1 crossed that boundary first, back in August 2012, becoming the first human-made object in history to enter interstellar space. Voyager 2 followed 6 years later, on November 5th, 2018, crossing through an entirely different section of the boundary, out on the flank of the bubble rather than through the front. Mission scientists confirmed the crossing almost immediately using onboard instruments, which detected a sudden, sharp drop in solar wind particles paired with a spike in high-energy cosmic radiation flooding in from outside. It was a historic, headline-making moment covered by outlets around the world for exactly one news cycle before public attention moved elsewhere. But for the small team of scientists actually monitoring Voyager 2's instruments day after day, this crossing turned out to be only the opening act. Because less than 3 months later, sitting quietly at their desks at the University of Iowa, they picked up something nobody had fully prepared for. The instrument responsible for this discovery is called the Plasma Wave Science System, designed decades earlier by a team led by the late Dr. Donald Gurnett, one of the most respected space physicists of his generation, a man who spent much of his career waiting patiently for exactly this moment. The instrument works using 2 10-meter antennas, extended out from the spacecraft's body in a wide V shape, effectively turning Voyager 2 into an extraordinarily sensitive receiver, not for radio signals in the way most people imagine, but for the natural electrical oscillations of plasma, the ionized charged gas that fills the space between stars. Here's the key physics behind it. Us, and it's simpler than it sounds. When plasma gets disturbed by an outside force, its free electrons vibrate at a very specific, precisely measurable frequency, one directly tied to how dense that plasma actually is at that exact moment. Denser plasma rings at a higher pitch. Thinner plasma rings lower, almost like plucking a string and listening to the note it produces to figure out how tightly it's wound. It's a real, well-understood relationship. One physicist had confirmed in controlled laboratory conditions for decades, but one nobody had ever been able to directly measure out in true interstellar space, simply because no instrument had ever physically been out there to listen, until Voyager 2 finally arrived. On January 30th, 2019, at a distance of 119.7 astronomical units from the Sun, roughly 11 billion miles, Voyager 2's plasma wave instrument detected exactly this kind of event, a plasma oscillation, ringing clearly in its 1.78 kilohertz channel. Scientists ran the numbers, and the resulting density measurement, 0.039 electrons per cubic centimeter, was roughly 20 times higher than the plasma density typically measured just inside the heliosphere in the region Voyager 2 had left behind only weeks earlier, 20 times denser in an instant. This single frequency became one of the clearest, most direct pieces of confirmation that Voyager 2 truly had crossed into interstellar space, a real, physical measured signature of a spacecraft standing somewhere no human-made object had ever stood before, except for its own twin, 6 years and a completely different trajectory earlier. But scientists didn't stop listening after that first tone faded. And a year and a half later, the frequency changed in a way that raised even bigger questions than the first detection had answered. On June 19th, 2020, now at a distance of 124.2 astronomical units, several astronomical units farther out into the dark, Voyager 2's instrument detected a second plasma oscillation event, this time ringing noticeably higher at 311 kilohertz. Translating that frequency into density gave a reading of approximately 0.12 electrons per cubic centimeter, nearly 3 times what had been measured barely 18 months earlier and several billion miles closer to home. The plasma out there wasn't uniform, it wasn't static, and it wasn't random. It was getting denser steadily the farther Voyager 2 traveled, forming what scientists now call a radial density gradient, a structured directional pattern built directly into the fabric of the space surrounding our entire solar system. And when researchers compared this pattern to what Voyager 1 had separately detected years earlier on a completely different side of the heliosphere, hundreds of millions of miles away, they found the exact same underlying trend. 2 spacecraft, launched the same year, traveling in 2 completely different directions, decades apart in their individual crossings, both independently confirming the same structural truth about the region of space our entire solar system is quietly drifting through. It's worth pausing here to understand that Voyager 2's plasma wave instrument wasn't hearing something completely alien to its own history. This same instrument, or rather its earlier version working inside the heliosphere, had already picked up strange ringing tones decades earlier, back in the early 1980s, when it detected what scientists came to call the solar wind termination shock, the inner boundary where the outward rushing solar wind first begins slowing down as it runs into resistance from the surrounding interstellar medium. Then, between 1992 and 1994, both Voyager spacecraft, still traveling well within what was believed to be the outer heliosphere at the time, picked up a series of low-frequency radio emissions originating from somewhere far beyond where either spacecraft had physically traveled. Scientists eventually traced those emissions to the heliopause itself, triangulating their source using the time delay between when Voyager 1 and Voyager 2 each detected the same signal. In other words, this wasn't the first time humanity had used these 2 aging spacecraft to listen to something happening at the true edge of the solar system. It was simply the clearest, closest, most direct version of a decades-long pattern, one where 2 40-plus-year-old machines kept accidentally proving they were built better and were listening harder than anyone in the 1970s had any right to expect. There's also a companion discovery worth knowing about, because people sometimes confuse the two, and it's worth setting the record straight. In 2021, researchers at Cornell University, working with data from Voyager 1, not Voyager 2, identified a separate, much fainter phenomenon, a persistent low-level plasma hum, ringing continuously since around 2017, distinct from the sharp, event-triggered oscillations Voyager 2 detected in 2019 and 2020. That hum, coming from Voyager 1's side of the boundary, revealed a kind of constant low-amplitude background noise in interstellar space, present even without a solar shockwave triggering it. Voyager 2's discovery is different, and in some ways more dramatic, precisely because its frequencies aren't a constant background murmur. They're sudden, discrete, clearly triggered events, direct responses to specific, identifiable eruptions from our own sun, arriving months after the fact like distant thunder, finally reaching you long after the lightning flashed. Together, the 2 spacecraft are building an entirely new picture of interstellar space, one with both a quiet, steady hum and sudden echoing rings layered on top of it, and Voyager 2 happens to be responsible for the more explosive half of that picture. Now here's the detail that tends to genuinely stop people in their tracks once they actually understand it. These frequencies are not some kind of constant ambient background hum, quietly playing on a loop out there forever, waiting to be picked up whenever a spacecraft happens by. They are triggered actively by shock waves, powerful pressure waves unleashed by coronal mass ejections, violent eruptions exploding off the surface of our own sun, sometimes without warning. These eruptions blast outward through the entire solar system, cross the heliopause, and then keep traveling through interstellar space for months, sometimes over a full year, before finally slamming into the surrounding interstellar plasma, billions of miles from where they originally erupted. When that impact happens, it excites the electrons in the surrounding gas, forcing them to oscillate at their own natural resonant frequency, which is precisely the ringing tone Voyager 2's instruments are built to detect and record. Every single frequency Voyager 2 has picked up out there is, in the truest possible sense, a delayed echo, an echo of a solar outburst that erupted from a star 93 million miles from Earth, traveled outward for the better part of a year, crossed the invisible wall separating our solar system from the rest of the galaxy, and finally rang out in a place humanity had never before been able to listen to directly, until now. Sit with that for a second, because it's genuinely strange once you actually think it all the way through. Our sun's violent outbursts, its unpredictable temper, are physically reaching places we once assumed were completely sealed off. Cut off, disconnected from anything happening back home near Earth. They're vibrating the literal fabric of interstellar space itself, more than 11 billion miles from where they originated. And this isn't a one-time fluke, either. It has happened repeatedly since, with additional smaller events detected in the years that followed, including further readings picked up in 2021 and beyond. That means the edge of our solar system isn't some silent, motionless, sealed wall the way most people casually picture it in their heads. It's an active, responsive membrane, one that physically rings every single time our own star loses its temper, and by pure chance, an aging, plutonium-powered spacecraft launched during the Ford administration happens to have a front-row seat to every single performance. Let's be completely clear about one important thing here, because it genuinely matters. This is not a signal from an alien civilization, and it is not any kind of intentional transmission aimed at us or anyone else. It is a naturally occurring physical phenomenon called plasma oscillation. The same basic underlying physics you'd find inside a fluorescent light bulb or in Earth's own upper atmosphere, simply happening in a location that no instrument had ever been able to measure directly before Voyager 2 got there. But honestly, that fact makes this more astonishing, not less. This is the literal physical sound of the true edge of our solar system reacting, in real time, to activity happening on our own sun, captured and translated into readable, usable scientific data by an instrument engineered using 1970s technology, running now on a power source that measurably loses output year after year, decade after decade. Consider what it actually takes for a discovery like this to even reach us in the first place. Voyager 2 is now so distant that a message sent from Earth, traveling at the literal absolute speed of light, takes over 18 hours just to arrive, and the same span again for any response to travel back, meaning a single question and answer exchange with the spacecraft eats up the better part of an entire day every single time. Its transmitter broadcasts using less power than a household refrigerator light bulb, and NASA depends on radio dishes wide enough to swallow a football field just to detect the faintest possible whisper of a signal by the time it finally crosses that distance and reaches Earth. Its power source, a carefully shielded block of steadily decaying plutonium, loses roughly 4 watts of usable energy every single year. A slow, permanent decline that has already forced mission engineers to shut down several onboard instruments, one after another, over the years, simply to preserve enough power to keep the spacecraft's most essential systems, including this exact plasma wave instrument, alive just a little longer. And this discovery is not just a scientific curiosity to file away and quietly forget about. It is actively reshaping how researchers understand the true boundary of our solar system and the region immediately beyond it. Knowing that the interstellar medium surrounding our sun isn't smooth or uniform, but instead structured, layered, and directly responsive to solar activity happening light hours away, changes how scientists calculate radiation exposure risks for any future deep space mission, and how they model the environment that any future interstellar probe would actually have to physically survive out there. It also feeds directly into one of the biggest open questions in modern astronomy right now. Exactly how do stars interact with the material immediately surrounding them? And what does that ongoing interaction actually mean for the habitability of planets orbiting other distant stars scattered across the galaxy? Every single exoplanet making headlines today, every distant world being scanned for the faint chemical signatures of life, sits inside its own version of this exact kind of boundary, generated by its own star. And Voyager 2's frequency detections remain some of the only direct, physical, in-place measurements humanity has ever gathered of what a boundary like that actually behaves like under real conditions, out past the edge of anything resembling a controlled laboratory. It's also worth remembering that this discovery didn't happen in isolation, sealed away inside a physics journal nobody outside academia ever reads. NASA scientists have openly said that data like this is directly shaping the early planning for a proposed future mission, sometimes referred to as the Interstellar probe concept, a spacecraft that would be purpose-built from the ground up to study exactly this region, carrying far more advanced instruments than anything Voyager 2 launched with in 1977, and potentially traveling faster and farther than either Voyager ever could. In other words, Voyager 2 isn't just making history, it's actively writing the instruction manual for whatever comes after it, decades before that next spacecraft even leaves the launch pad. Every frequency it catches, every density gradient it measures, becomes a data point some future mission planner will eventually rely on to decide exactly where to point humanity's next set of instruments and what to expect once they get there. There's also something quietly emotional about all of this, if you let yourself sit with it for a moment. Voyager 2 was built by a generation of engineers using slide rules and punch cards, launched during a decade when nobody was entirely sure it would survive its first flyby of Jupiter, let alone outlive the careers, and in some cases the lives, of the very scientists who built it. Its plasma wave antennas, two thin 10-meter rods extended out into the vacuum, have been silently, patiently listening for nearly 50 consecutive years, through flybys of 4 planets, through the crossing of an invisible boundary nobody had ever crossed before, and now through the discovery of a frequency that reveals our own sun's temper rippling out across a distance so vast that human language barely has the vocabulary to describe it honestly. Every one of us alive today will very likely be gone long before Voyager 2 finally goes silent for good. And yet, right now, tonight, it is still out there, still working, still catching sounds nobody on Earth has ever heard before it did. Voyager 2 is still out there tonight, drifting outward at more than 30,000 miles an hour, still occasionally catching the ring of another solar shockwave, finally arriving after its long, silent journey through the dark. NASA has already permanently shut down several of its remaining onboard instruments just to preserve enough power to keep the spacecraft transmitting at all, and current projections from the mission team suggest that sometime in the years ahead, its remaining systems, including the very instrument responsible for this exact discovery, may eventually run out of power entirely and fall silent for good. When that day finally comes, this particular window into the true sound of interstellar space closes, at least until humanity manages to build something new, something capable of following Voyager 2 out into that same silence and picking up the listening right where it left off, decades from now. Think, too, about the sheer number of people it takes to keep a machine like this alive, generation after generation. Many of the engineers currently commanding Voyager 2 were not even born when it launched. They inherited a spacecraft, a set of instruments, and a decades-old command language from mentors who have since retired or passed away. And they now carry the responsibility of deciding, instrument by instrument, watt by watt, which parts of this aging machine get to keep functioning and which parts finally have to be switched off for good. Every frequency Voyager 2 catches from here forward is the product of that quiet, ongoing act of stewardship, an unbroken chain of scientists passing a 50-year-old torch from one career to the next just to keep listening a little longer. So the next time someone tells you that NASA confirmed Voyager 2 is picking up a frequency from outside our solar system, understand exactly what that really means. It is not contact. It is not a message meant for us, and it never was meant to be. It is something quietly more remarkable than that. Direct, measured proof that our own sun's violent outbursts are physically rippling past the edge of everything familiar to us, ringing through the true, absolute emptiness of interstellar space, and being caught, decoded, and understood by a machine humanity built nearly 50 years ago, still transmitting, still functioning, still teaching us things about the universe that no textbook could have predicted in advance. From a distance, most of us will never fully be able to comprehend. If a nearly 50-year-old spacecraft running on a slowly dying power source can still catch the echo of our own sun ringing through deep space, imagine what else is quietly waiting out there in the dark to be discovered. Subscribe now so you never miss the next mystery from the edge of the universe.